Good morning, everyone. I'm Juntae from Seoul National University of Science and Technology. Today, I'm going to talk about Gaussian TinyYOLOv3 Accelerator. So let's get started. The contents is as follows: introduction, proposed architectures, experimental results, demonstration, and conclusion. And the first is about motivation. There is a growing demand for object detection applications in mobile and edge devices. So as you can see, automobile driving and product counting in market and the farm surveillance systems and construction site surveillance systems. So there are a broad variety of applications. So its demand is highly important. However, highly accurate and high throughput and highly power efficient object detection accelerators in mobile and edge devices still need enhancements because there are a lot of constraints, and in reality, the GPU consumes a lot of power, and so we need to develop the mobile and edge devices. So there are a lot of object detection algorithms, but in this case, we select the YOLO models, which stands for the you only look once YOLO, because the YOLO models are famous one-stage object detections and are used in a wide range of applications. However, there is a problem. There are a variety of YOLO models, but a lot of models has a lot of complexity. And so, for example, you can see the structure of YOLOv3, and it has a lot of sticky connections and feature permanent networks. And it causes a lot of constraints when we implement it in the hardware level. And YOLOv3, it also has a lot of sticky connections and complex. And also YOLOv3 is getting more complex. So we need to focus on a simple model and while managing the highly accuracy. So we selected the TinyYOLOv3 model as our target model because it has a relatively simple complexity while maintaining a good accuracy. So as you can see, it has only 2 sticky connections, and yeah. So next is the proposed architecture. Here is our entire diagram. As you can see, here is a global controller, and it manages to control over a system. And you can see the layer module plot. And unlike traditional architecture, we designed our architecture as a streamlined architecture, which can generate a high performance with regard to the output performance, because it can implement all dedicated layers, and each module has its own role, and it generates each output, and it propagates the output, and finally it could achieve the high throughput. So before we dive into that, let's talk about the 3 metrics: accuracy, speed, and power. First, speed. In terms of speed, we need to improve the throughput or decrease the latency, and we focus on the improve the throughput. So as I said before, we implemented this architecture as a streamlined architecture, so we could achieve the high throughput. And in terms of power, we adapted the power efficient operators instead of the traditional accurate operators. So by doing that, we decrease the power consumption. And finally, in terms of the accuracy, we improve the accuracy by adapting the Gaussian YOLO algorithm. And let's talk about the layer processing unit first. It performs all the required operations for each layer. So it consists of the following modules: buffer, sliding window, convolution, batch normalization, liquid value, quantization, and max pooling. And they are implemented differently according to the layer. For example, if it requires a max pooling unit, then the max pooling unit will be implemented in the layer processing unit for the module, for the layer. But if that model if one module doesn't require the maximal unit, then it will be eliminated when it is standardized. So as you can see, here are two parameters. One is for the TI and one is for the TO. They stands for input tiling and output tiling. Each parameters is used to change it or change the parallelism, because as you can see, each layer has different computation laws. So, but our goal is to implement all the dedicated layer modules. So we need to balance the design. So in order to balance the design, we made these parameters, and we balance the design by changing these parameters. And let's take a look at the convolution processing unit more deeply. The convolution processing unit receives 8-bit fixed point activation and 8-bit fixed point wait, and then it performs the convolution, and it performs the multiplication and addition, and then it passes the output to the BIOS module and liquid level and quantization. But here is our critical contribution. This part. This part is about hardware-friendly shift-based floating fixed map and quantization. As you said, as you can see, it receives the 8-bit fixed point and 4-bit floating point. Unlike traditional fixed multiplication or integer multiplication, we adopted the idea of multiplying those two different types. One advantage is that by adopting this idea, we need only 8-bit and 4-bit multipliers instead of 8-bit multipliers. So we multiply them, and all we need to do is to just shift it to some amount of this exponent value. So by doing that, we can decrease a lot of amount of hardware resources, and it also decreases the required latency. And as you can see, we proposed this equation. This equation is used to obtain the shift value. How many shifts we have to shift? So as you can see, it consists of AS minus IS plus M minus E minus B, and each variables stands for this information. But after a lot of experiments, we finally realized that if we only change the AS value as similar as possible, then we could minimize the drop of accuracy. So finally, we decreased the average accuracy. It only decreases the average accuracy by 0.05%. So let's back to the convolution processing unit. In terms of hardware-friendly unit, we adopted the approximated shift-based liquid value. Instead of the commonly used alpha value of 0.01, we utilized the approximate value 0.09375, which is a combination of 2 to the negative 4 plus 2 to the negative 5. So by doing that, we also decrease the huge amount of hardware resources. And finally, in terms of accuracy, we adopted the Gaussian YOLO layer. This is a traditional YOLO layer. It consists of class scores, object scores, and B-box coordinates. But unlike this traditional YOLO layer, the Gaussian YOLO layer adopts the Gaussian YOLO algorithm to the B-box coordinates. So by adopting that, when we determine the output results, we can utilize the Gaussian parameters of B-box coordinates, and it contributes a lot of increment of accuracy. So it increases accuracy by 0.8% to 1.2%. and also it negligible amounts of increased loss. So it is quite reasonable. Finally, here is a design summary. This part for the speed, this part for the power efficiency, and this part for the accuracy. And now let's take a look at the experimental results. Here's our experimental results in terms of the hardware resources. So the first thing is about the where to be fixed map, and the last thing is our proposed map. As you can see, in terms of LOT flip-flop carry 8, we achieved the high efficiency, and also in contrast with the previous study, we also improved the efficiency. And in terms of accuracy, we experimented both COCO and Pascal VOC dataset, and each dataset we achieved the 0.91% and 0.48% respectively. So it is quite well-made model. And finally, here's our overall comparison results. Here's our proposed model, proposed accelerator, and previous results are as follows. And as you can see, we consume a relatively large amount of on-chip memory, or DRAM. However, it achieved the highest accuracy over the previous studies, and also it achieved the highest throughput or speed in terms of FPS or throughput. And as you can see, it consumes a relatively large amount of power compared to the previous studies. However, in terms of power efficiency, GOPS per watt, it achieved the highest power efficiency. So here is our results. And finally, let's take a look at the demonstration video shortly. Yeah, this is a laptop, and here's our FPGA, and they are connected through the USB 3.0 interface. And the bitstream file is stored in the flash memory, and when we turn on the device, then it automatically downloaded the bit file and program it. And after that, enter the simple formula command. And after enter the command, it tested the communication, and after passing the communication test, it showed the simple window. And as you can see, it detects the person and smartphone, and also it detects the laptop, and finally it detects the monitors and chair. So this is a very simple version of the demo, and let me conclude our design. We proposed a dedicated FPGA implementation of a Gaussian TinyYOLOv3 Accelerator using a fully pipelined, streamlined architecture with a hardware-friendly shift-based FF-MAC operator. Also, our design achieves the highest accuracy, FPS, and power efficiency for TinyYOLOv3. So thank you for your attention, and if you have any questions, feel free to ask me.